So we are moving on to the second session for today with Dr. Pascal Halffmann from the Fraunhofer Institute for Industrial Mathematics. Those of you who are new to this program this year, Fraunhofer Institute is one of the largest industrial research organizations in the entire world. And Fraunhofer has been the leaders in a lot of inventions. You might have heard about airbags. Fraunhofer was the one who invented them. White LEDs, again, coming from the Fraunhofer Institute. MP3 data type for a lot of your audio files. And we have today Dr. Pascal Halffmann joining in from Fraunhofer ITWM to talk about the state of quantum optimization and with a more focus on practical applications. A little about Dr. Pascal. He holds a PhD in mathematics and is currently the research coordinator for quantum computing activities at Fraunhofer ITWM in Kaiserslautern, Germany. His research is focused on quantum computing and optimization, with applications ranging from finance to energy. In particular, he has provided substantial results on quantum algorithms for application-oriented optimization problems. All in all, he's an amazing lecturer. He was also a participant and one of the key lecturers in our last year's program. If some of you are joining in again this year and remember last year's program, Fraunhofer was also one of our contributing project partners. And that project ultimately translated into a QSL project. Many of the fellows worked with the Fraunhofer team and are currently publishing the papers. So it's really very exciting, and I'm honored to invite Dr. Pascal again. I'm sure you would have a lot of fun in the next 30 minutes or so. So with that, over to you, Pascal.
Thank you very much. That was a really, really nice introduction. I'm flat up that I'm a wonderful person. So you are too. So thank you really much and very much to that for the invitation here. I'm really proud and also really delighted to provide like a small lecture here. I'm from the Fraunhofer Institute for Industrial Mathematics, which is part of the Fraunhofer Society. So we are indeed one of the leading applied research organizations in the world with over 76 institutes, 30,000 employees, and over 3 billion of business volume. We do a lot of patents and we have a lot of successful spins off, even over 500 since the 2000s. With also institutes in the international area ranging from the US to Singapore. And our mission is to provide research-based decision-making for the industry. That is, we transition fundamental hot news research towards the industry to provide like ready-to-use solutions for our industrial partners. Our name comes from Josef von Fraunhofer, who was both a researcher, an inventor, and entrepreneur, and that is exactly the intersection we as Fraunhofer see as our mission. One part of the Fraunhofer Society is the Fraunhofer Institute for Industrial Mathematics, and our mission is to provide industry solutions via our mathematical expertise. That is, we everywhere where mathematics is involved, we are there to provide you with a solution based on our mathematics. So, and that hopefully for a good future. And this includes the automotive sector, finance, the energy sector, also material science, engineering, optimization, transport, logistics, also next generation computing, healthcare, transportation, and obviously quantum computing. And for quantum computing, I'm the research coordinator of our activities there. And we have two, I think, missions. First of all, we want to make quantum industry ready. That means we want to accelerate quantum computing so it can provide utility for the industry. But on the other hand, we want to raise awareness for quantum computing at the industry to see, okay, there's a new player around that could benefit massively from in your day-to-day business at one point. And we focus on several parts. We have, for example, two main use cases. This is finance and material science. And we use both optimization and AI to enhance quantum computing and vice versa, enhance quantum computing in optimization and AI. And we do that not just solely with quantum computing, but also with the integration of classical, for example, high performance computing hardware. Yes, so today's topic, after this short introduction, is obviously optimization problems. For those of you that are not fully familiar with optimization problems, I'll give you a short recap. So a general optimization problem consists of of course, a function we want to optimize. In this case, for example, minimize. And this can be a linear, a quadratic, or even like a totally non-explicit, non-linear function. And we have some side constraints. For example, we have equality constraints and inequality constraints. And these functions could be likewise linear or non-linear. And we have some decision variables that could be continuous, integer, or even both, that we have like a mixed integer problem here. And these optimization problems occur everywhere. I mean, you could just go to Google Maps and find the shortest path to your grocery store, then you have solved an optimization problem. I bring two interesting optimization problems with you. One is a rather famous one, the traveling salesperson problem, where you want to find an optimal, like with respect to the distance route, visiting, for example, all given cities exactly once, and then you return to your starting point. For example, a small example, we have all state capital cities in the US, excluding Alaska and Hawaii, because it's a bit difficult to get if not to not cross any borders. And of course, so if you check for all of these possibilities, this is like 48 times 47 times 46. So is quite a lot, but nevertheless, with our current optimization solvers like Gurobi and your usual laptop, you can solve this problem in 5 minutes. Similarly, I have brought another application from the energy industry. This is the so-called unit commitment problem. We want to find an optimal planning of our power plants that produce our electricity, with which we want to satisfy, obviously, our energy demand. But of course, we want to minimize the production cost of our energy, and we want to satisfy the properties of our thermal units. That is that, for example, a nuclear power plant cannot be easily switched off and on, but you have to run it, for example, a certain amount of time. And each power plant has obviously a certain capacity of energy it can produce. And then you get, for example, a scheduling over 24 hours where you say, okay, I produce at hour 5 this amount of coal and electricity, and I produce with gas this amount of electricity, and so on. So, and with a little bit of experiment on our side, we have conducted that even with 2,500 units and different load capacities, you can solve this problem with commercial optimization solvers in under 5 minutes. So it's, even though, and this is the important factor now, both problems are seen as NP-hard problems. That's one of the toughest problems you will face in optimization, meaning that those problems cannot be solved in polynomial time, but the problem or solution time scales exponentially. But still, these can be solved rather quickly. So just because an optimization problem is NP hard, it is not necessarily hard to solve in practice if your size is not that large. So, and it's mostly said that quantum computing and quantum optimization can provide a solution somewhere where we have faced NP hard optimization problems. But this is not entirely true from my point of view, because the bar, as you can see, is set really high to even provide quantum utility or foremost quantum advantage to these problems. So quantum computing has, of course, the potential, but the classical side is really strong here. So what do we do now? Well, there are some quantum algorithms that perform really well. The most famous one is probably quantum annealing. This uses adiabatic evolution. That means we transition from a well-known quantum system where we know the lowest energy state, and the lowest energy state is the one that represents our optimal solution. And we transition this slowly over to our problem formulation that is also encoded as a quantum system. And with the slow transformation, we remain in the ground state. We use this one, and we also use quantum tunneling. That means we can, from one energy state, we can tunnel through such a peak without going over it, but that, so we spare a lot of time, and also we can, from a local minima, get to the global optimal easily. Then we have the variational quantum eigensolver. This is a quantum circuit consisting of so-called parameterized gates. That means we have gates in our circuit that have a certain parameter. And then the goal is that we run the circuit, measure it, and then optimize using a classical solver these parameters until we found the optimal solution. The quantum approximate optimization algorithm is a combination of the previous two because it's a specialized variational quantum eigensolver that mimics the quantum annealing approach, but instead of this continuous adiabatic evolution, we discretize this. And lastly, this is a bit of a more exotic approach, is the Grover adaptive search that uses the famous Grover search algorithm, which is originally intended to find an item in a list by marking it and amplify its probability in the quantum circuit. But here we now mark all items that have an objective function which is lower than defined threshold. And once we have found such a solution, we update our threshold and go even lower. Yes, so to capture this fully. So this is how the VQE looks like. And this is like the QAA, where we have two specialized parts of our quantum algorithm, the problem unitary and the mixer unitary. And we alternately apply these in the quantum circuit and also update our parameters using a classical solver. And here's a small example of Grover adaptive search. So how well do these quantum optimization methods perform? Well, starting from the back with the Grover adaptive search, well, this one performs rather poorly at current quantum hardware because it provides a really lengthy quantum circuit. So we have a deep circuit, and it's hard to execute this on current hardware. So this is rather an exotic one for the moment, but could be interesting once we have reached fault-tolerant quantum hardware. The VQE and Quawa, the most promising ones because they can be executed on any hardware and also right now, but also leave room for fault-tolerant quantum computing where we can build more elaborate quantum circuits. And lastly, quantum annealing, which is a specialized quantum approach and only works on specialized quantum hardware, for example, as the D-Wave quantum computer, where we have seen, and this is where we have seen some major updates in the past year, that, for example, D-Wave proposes quantum supremacy, that they say, okay, we have solved a problem on our D-Wave quantum annealer that a classical computer takes ages for. And they also provide two interesting use cases, for example, to optimize training for drug discovery with Japan Tobacco, or they also collaborating with Volkswagen to navigate, to provide a new navigation system for their vehicles in their production cities. But this is what D-Wave is proposing, and well, it's hard to prove that they are correct. We did our own experiments and we took like a little bit different course. And if you just check here in this red table that for our unit commitment problem, which is with rather small instances, we see that our classical solver can solve this in milliseconds, where our quantum computer takes a bit more of approach, but provides barely the optimal solution and gets like really poor quality once our instances get even larger. So this is somewhat of a problem, and also we optimized our algorithm to at least get down with the result quality, but that obviously topples up our running time, as you can see in the graphic below. So one could, of course, argue our algorithm might not be optimal. DWAF has a better knowledge of their quantum computer. So I think that the current state is somewhere between having like no utility at all, but also not the supremacy that they are targeting at. But also, I would say to come back to the NP-hard problems, just because the NP problem is NP-hard is not sufficient to provide a quantum advantage here. Indeed, I will now quickly showcase 3 problems where it's more suitable that we find a utility because those problems are even harder to solve classically. And also on top of it, these problems feature features that usually occur in real-world problems. The first one is multi-objective optimization problems, where we have multiple, often conflicting objective functions. And these often occur, for example, in portfolio optimization, where you want to optimize your return, but also you want to minimize your risk. And here we have it that there is no clear optimal. If you have two objectives here that you both want to minimize, it's not clear if this solution is better for you than this solution. And therefore, we came up with a different notion of optimality in this field. And this is the so-called Pareto optimality. And this states that an image is optimal if there's no other image that is better in every objective function and strictly better in at least one. And with this information, you can say, okay, this solution down here is not Pareto optimal because this solution is better in both objective functions. On the other hand, this solution here, there are obviously solutions that are better in the first objective function, meaning all those here, but none of these have a better objective function value in the second objective function. If you want to know more about this, there's a nice book by Matthias Ergot, Multi-Criteria Optimization, that provides a good start to this. And basically, here, colleagues of mine have found that there is indeed quantum utility because they have a rather simple quantum algorithm here, and they have a pre-trained QAA they are using and providing random samples from this, and they show that this can indeed provide a better or even equivalent good solution than classical solvers. So this is a really nice result here. Another way is to look at it is robust and stochastic optimization, where we on the one hand have like an uncertain parameters, for example, the wind energy production in the unit commitment problem, and we have a set of scenarios and we want to find a solution that is robust against changes and thus works well in every scenario. And for example, we can define this robustness by looking at, okay, I want to optimize the worst case performance over all scenarios for my solution. On the other hand, stochastic optimization has random variables given, and we want to find an optimal solution to our objective function. But since we have random variables, we restrict ourselves to find something like the expected value of our function. And for the first one, we ourselves have provided a nice approach where we say, okay, we take the samples we are obtaining with our DWF quantum computer for a deterministic problem and then check which of those solutions we obtain is the best one against our different scenarios. And this provided quite well results already. And at last, we have the multi-stage, multi-level, and other complex problems. For example, multi-stage problems consist of two or more sub-problems that have to be solved consecutively. So you have one decision made, and then you feed this decision in your next problem, and you have to optimize again. Multi-level problems are even indeed harder because then a problem has one or more sub-problems in it that need to optimize once every time you evaluate your solution. So a prime example for the latter one is the transportation problem, where you, for example, have a city and you want to provide a new public transport, for example, a bus. Then you have to set the bus stops, then you have to assign those bus lines, and you have to provide schedule for each of these. And as you might know, if you, for example, want to have an optimal with respect cost public transport, then of course a change in the bus lines can also trigger a change in the bus stops because there is room for optimization. So this is a really complex and multi-level problem. And I was recently on a conference, and there they showed that with quantum computing, you cannot you don't have to look at this problem sequentially, but you can solve as a whole, proving there that you also have the prospect of quantum utility. And with that, I'm at the end of my talk. Thank you very much for having me here. Thank you very much for listening. And if you have any questions, just shoot at me now.
Thank you so much, Pascal. We've got some questions coming through on Discord, and then I can pass those on to you from the students. I guess while we wait for some of them to be typed up, because I can see people typing, is there, I guess, the kind of three takeaways you'd want the students to have after the end of this session?
Well, first I would say the main takeaway of my talk is, okay, we have NP-hard problems that are seen as hard from a theoretic point of view, but in practice, in our practice everyday life, these are not as hard as you think, because we have 60, 70 years of optimization techniques, and it's hard to overtake this with the newly and not perfect quantum computing here. But there are problems, and this is the second takeaway, that are extremely hard, and we don't have these commercial solvers like Gurobi that exist for these kind of problems, like multi-objective problems. So there is indeed more probable prospect that quantum computing will succeed. And the third one is we always have to check not for the algorithm or the hardware itself, but the quantum algorithm plus quantum hardware is the benchmark against classical systems.
Thank you. So we do have a question that has come in. So this is from James in New York City. Which problems exactly do you suspect quantum computers will excel at?
I would suspect that especially stochastic optimization problems that you, for example, that often occur, for example, in portfolio optimization, portfolio like portfolio theory and so on, will succeed, because this is a stochastic system. A quantum computer and a quantum system itself is a stochastic system. So there is a close relationship here. And also, since it's finance, there is obviously a lot of efforts and a lot of money and a lot of gain for you there. And that is why big companies like JP Morgan Chase have elaborate quantum departments that work effortlessly on these kind of topics.
Thank you very much. Peter from Nigeria is asking, what are the yardsticks we need to use to ascertain D-Wave's proposed quantum advantage?
Well, first of all, you need probably your own D-Wave device, because they, and also maybe 10 to 15 years of expertise in working with that device, because I've worked with them together at some point and they know their machines really well. So you have to, and also when you have access to their devices, this is like publicly available, or at least behind some pay border. But if they do their experiments, they have a perfectly trained and perfectly calibrated system that you probably won't have with your access. So this is one part. And of course, they are shown the quantum supremacy in what they label as a practical problem, but this problem is really close to their architecture. So this is also a main advantage. I think these are the main topics, or the main reasons for this. They have a perfectly calibrated system. They know what they're doing there. And on the other hand, the problem they are looking at is perfectly fitted to this architecture.
Thank you. All right, so we've got one more question that is, would it be better, let me just rephrase this, would it be better for user optimized hybrid algorithms, or is it more efficient for an entirely independent algorithm that is native to a specific hardware?
Well, I'm a big fan of hybridization. I think that even if you look at only like one optimization problem, that there are parts of it that can be worked well on the quantum system, and other parts can be really worked well on a classical system. So hybridization is, especially in the current area of NISQ devices we are still at, is the way to go. And as you can see, QAOA and VQE are both hybrid algorithms in my mind, since we need a classical solver.
Thank you. Siri from Texas is asking, how can quantum be used in real-world businesses? For example, how would an established company integrate quantum into their business?
Well, I've visited some of D-Wave keynotes, for example, where they, as I showed you in one of my slides, they have really worked with companies in their data and at least they tell you so, that they have provide quantum solution to like their practical day-to-day problems. So that of course leaves you with two options if you want to do that. First of all, either you buy a quantum computer for your company. Of course, this can be possible for large companies, but for smaller and medium business entities, this makes no sense. But there you have to rely on cloud access. And I would say that the latter one is the thing that works well, especially since many supercomputing centers are working effortlessly to integrate quantum computers in their supercomputing centers. That means we have a quantum and HPC orchestrator there. And I think this is where we will benefit from in the future and where companies will benefit the most of it.
Thank you. Arthur from New York City is asking for portfolio optimization with a single objective function. Will there be a quantum advantage over Groby?
I highly doubt it, especially since the original portfolio optimization problem, if you go by Henry Markowitz, is a continuous optimization problem. And with continuous optimization problem, we would have to discretize our continuous variables as of now to the quantum computer, or we have to use different specialized encodings. For example, we have an angle encoding instead of a simple qubit encoding here. So, and of course, this single objective problem is indeed easy to solve. So I wouldn't expect their quantum advantage. I would expect a quantum advantage either if you have multiple objectives or you have, for example, some different uncertainties in your parameters, or you have some extra constraints you need to respect.
Thank you. And I think we have time for one final question. So this is, there's no location, but this is from Arte. Are there any particular hardware platforms, D-Wave, INQ, IBM, etc., better suited for optimization use cases right now?
Well, D-Wave is well suited because the quantum annealer basically solves your quadratic unconstrained binary optimization problem, and it's specifically designed to do so. But of course, this comes with a caveat. This is a special purpose quantum computer, so you can only do this task. So everything has to be designed or changed such that it works for this task. And from like a research perspective, I cannot mingle with the quantum algorithm because the quantum annealing process is fixed. On the other hand, I would say that there are three interesting quantum hardware for universal quantum computers that are suitable. This is superconducting qubits, because they, from all the qubits that are out there, the most matured one, with IBM bolstering now our 1,000 qubits. The ion trap qubits have the advantage because in our quantum optimization problems, we need a more variable connection between where we can do entanglement between the qubits. And with the superconducting qubits, we are restricted to the architecture. So this can be an advantage there. And at last, we have the neutral atom ones, where we have these Rydberg atoms. And what they do in these analog quantum computer with the Rydberg atoms is solving a maximum independent set problem. And this is basically also an optimization problem. So there's also a really close connection there. So these are my three favorites. Currently, if you want to currently solve your optimization problem, I would restrict myself to D-Wave. If you need a specialized algorithm, you go to the superconducting qubits.
Thank you very much. Would you have time for just one more question? I know we're slightly over time.
That's okay for me. I
Yeah.
have time.
So Ron in Chicago is asking if anyone at Fraunhofer is looking into quantum optimization for the healthcare industry.
As I currently know, not really. So I know from colleagues that are working on other ways of quantum computing for the health industry, that is either in the detection of new drugs or in quantum sensing, where they're working on using magnet resonance therapy or thermometer to, for example, get an image of your brain. That I'm aware of, but especially for this, I'm not aware of. But we are currently checking this in our institute because we have a really strong optimization work group that, for example, has an elaborate algorithm for the use case in the healthcare industry, especially, for example, with cancer therapy, where you use radioactive material that you shoot at the cancer cells. And there you have a multi-objective problem where you obviously want to maximize the effect on the cancer cells, but minimize the harm on your healthy tissue, on your organs, for example, on your liver, on your brain, if there's any cancer cells nearby. And obviously, it would be rather interesting because it's a highly complex problem where we work together with physicists, with people from medicine, and so on, where you also have certain uncertainties. And it would be interesting to check whether quantum computing can be used to improve our algorithm there.
Thank you. We don't see that so much, do we? We see more the applications in finance or other, but not so much in healthcare for those specific problems.
But that's our mission. Our mission is mathematics for a good future.
Thank you so much. We've come to time. So thank you for your time today, Pascal. That was amazing.
Fantastic session. Thanks a lot, Pascal. And with that, we come to an end for today's sessions. Thank you, everyone, and have a great day ahead.